Hello, my name is Ryan White. My talk is entitled on the evolution of minimal volume sufficient probability sets for stochastic paths. Here at not actually the University of Oxford, but my home office instead. But the sort of problem that I've been working on to investigate is if you have a stochastic process, how can we trace the location where the random process probably is, which is not a very precise thing to say, but the thing that makes a bit of sense is to look for example, a set where there's a, say, 95% chance that the random process is there. Now, in general, there are lots of such sets, but the most interesting one probably is the one that has the largest minimum probability. So in other words, the smallest set that contains enough probability. So first, we're going to suppose that we have a probability space and a random variable. The random variable we're going to assume is valued in the d-dimensional real space. Nothing particularly important about the real space, but in most of the applications that I have in mind, this is what makes sense. And turns out there are some results that already exist that tell you about these minimum volume, high sufficient probability sets. In the next few slides, I want to just explain what already exists and then what I want to do next, and what I have done next so far. So if we fix some probability alpha, we can have this first thing with the script S. It's the set of all Borel sets where there's at least probability alpha that the random variable x is in that set. So these are all the sufficient probability sets. And then within that, I have this set M, another set of sets, and it's the minimum argument of the Lebesgue measure of a set M, such that M is in that sufficient probability set. So these sets M are called alpha minimum volume sufficient probability sets, MVSPs for short. And so basically we're just looking for the sets that have the very smallest Lebesgue measure, but also have sufficient probability. And a related idea that turns out to have a strong equivalence to these MVSPs is the superlevel set of a probability density function, small f. So here's just a small example. This is a standard normal random variable. We can see that I have several superlevel sets here. The set of x values where the PDF is above a certain level. So for a unimodal probability distribution like this, it's really trivial to see that, the one on the right, the level set at 0.05, which is -2 to 2, we know just from basic standard normal random variables that's exactly, there's exactly 95% probability in that, and it's clear intuitively that this is the smallest possible set. The interval from -2 to 2 is the smallest possible set where this happens. Now, this isn't a unique thing. There are, I could just make the interval closed instead of open, and I would still have a valid MVSP because it doesn't change the Lebesgue measure. It also doesn't change the probability. And so we can see. So this is for R1 for this particular example, but of course we can use Rn if we like. I think I was using D for the dimension. So to make this a little bit more formal, and to reflect some of the work that exists, what we can look at is the probability set density. And this D is a function that takes positive Lebesgue measure sets and maps them to essentially values of the PDF, between 0 and the maximum the PDF reaches, or the supremum at least. So then this D of B, it's the probability that the random variable is in set B divided by the Lebesgue measure or volume of the set B. So that's this probability set density, which I think if we look here, that's clearly what we're looking at. We're clearly looking at the sets that have the biggest density for the size of the set. So on the right there, the size of the set has a Lebesgue measure of 4. It's 4 units long. And it's the shortest possible one that has 95% probability in it. Now, all this seems a bit trivial, but just, again, want to review what exists. So then we also define a minimum volume class of sets. And what this is, it's a function that maps the probability alpha to the largest probability set density functions. And note here that some PDFs are going to fail to have this because it requires that the probability is strictly equal to alpha rather than at least alpha. So we can assume f is continuous, and that deals with it as long as also we're assuming it's differentiable, and the sets where it has 0 slope are small relatively. They're null sets. So in that case, we don't have flatness in the PDF, which generally allows us to have equality of probability. It generally allows sets to exist where that happens. Now, again, it's not; these aren't necessarily assumptions we have to make, but in order to have the strict equality, we need it. And in most applications that I have in mind, it doesn't really matter. And here are just some other examples that show that the sets in the MVC in that class are equivalent to level sets. And this is for a multimodal example. Both of these are multimodal, so it's a little bit less trivial. But again, it's fairly obvious for well-behaved functions that there's a certain equivalence between them. Another example in 2D, bivariate normal distribution. And so I essentially just cut out the MVSP for 95% by just sorting the heights of the PDF on a mesh and just picking out the biggest ones and just adding them and adding points until we reach 0.95. And it's pretty much what we would expect. On the right side there is just a diagram of the ellipse that is the MVSP. So pretty trivial, but this is computationally not so easy. For 2D, it's fairly fine, but when I try to go with higher and higher dimensions, which I would like to be able to do, I'm not going to be able to sort the PDF on a whole mesh. Calculating a PDF on a mesh might even be expensive. So I'll show you some other ideas that I've been working on to make this work better. Another example here, just to illustrate another 2D version. Same kind of thing. The PDFs on the left and the superlevel set that is an MVSP is on the right in blue. And so we can see in general it seems that superlevel sets map well to these MVSPs. And turns out this level set equivalence is pretty universal. In this paper from Garcia and friends proved this theorem that the superlevel sets must be in the MVC. They must be in that class of sets. And there's a one-to-one equivalence between them. And now, I don't want to go too much into their proof, but their proof works for probability mass functions with discrete random variables and even cases that don't neatly fit into discrete or continuous classifications. Then some similar work exists from Polonik from 1995, and it was a little bit more restrictive. It did require continuity, and prior work from just general analysis literature had already done this for continuous variables, for continuous functions rather, in many different times, including this paper. But if it's continuous, everything's easy. Whereas Garcia's result does not necessarily assume that. but in that literature, it's generally just referred to like optimizing set functions, which a probability measure is, technically speaking. So nothing here is really new yet. So what I want to do is something that is a bit newer, is to take that result from a random variable and try to exploit it for stochastic processes. That equivalence between the MVC sets and superlevel sets. So instead of a probability space, we've got a filtered probability space. The filtration is just a monotone increasing set of sigma algebras that converge to F as t goes to infinity. And if I fix t, if I fix time, alpha subscript 1, say, that's just a random variable. So obviously all those results still apply. So in that case, everything that we saw there so far, it applies to stochastic processes. But what we cannot easily do so far is to actually capture the time dynamics in the model, to actually try to exploit that to, to say something about these MVSP sets. And so a trivial example is Brownian motion in one dimension. It's a random process whose position at time t is a normal random variable with variance t time. So trivially, we can find these, for example, 0.95 MVSP sets as time progresses. So from left to right, time is progressing. And the mean is still 0, but the standard deviation grows over time. And here we can do it totally trivially because we have this essentially knowledge that for a normal random variable, the area between plus or minus 2 standard deviations is roughly 0.95. And it's fairly easy to invert this thing to find numerical approximations when that's not possible, or express it in terms of an error function. So it's very easy in this case. We can say the MVSP indexed by time here is negative 2 root t plus 2 root t, because root t is a standard deviation. Very, very trivial. And back to this picture. This suggests a method for finding the MVSP. Just start a horizontal line, or plane or hyperplane in more dimensions, at the mode of the distribution, at the maximum of the PDF. And then just bring it downward. And as we go down, we capture more and more points on the x axis, and we can build our MVSPs by only considering these superlevel sets, which are generally easier to analyze. So yeah, superlevel sets, as that theorem says, it clearly works for Brownian motion because it's a very trivial, simple stochastic process. So theoretically, this all works. If we look at this, as time progresses upward, we see the level sets in blue getting larger and larger because the set is, or the random variable, random process is likely to be further and further away from the center the more we run time forward. So this is just a trivial example. What I want to do is to do some similar sorts of modeling for a problem in queuing theory I've been studying with some collaborators. And it's a fairly complex queuing system. And we've got some kind of queue here in the diagram. You can see, like, at these times, T1, T2, T3, and so on, batches of customers arrive, that they arrive at a processor to have some work done. And then at some points we have drops in the process where random batches of customers have been serviced. And so these are entering customers and exiting customers. Q subscript t is the just queuing process at time t. It's just how many customers are in the queue at a specific time. So the type of queue we've been studying is an MXGY1 queue. meaning it has Markovian arrivals, meaning the customer arrival times, the T1, T2, and so on, are Poisson process. And X is a random variable that tells us the batch size of customers arriving. The G there means the service time has a general distribution, so we're not assuming anything yet. And Y means it's serving in batches, and 1 means there's one server. So relatively well studied queue. The batches are not quite so well studied, but a lot of literature exists. But what we're doing that's new is to add several operational policies that try to mitigate some problems that cause a queue to not work and really efficiently. So there are a couple of problems we try to address. Switchovers, meaning turning the system on or off, can be very costly or slow or otherwise undesirable, can have an effect on the device sometimes, degrading it over time. And another problem is that when we turn the system off, although we're maybe saving some resources by not having it running for no reason, we still have something that's just totally underutilized if it's turned off. So our goal is to minimize switchovers and also do some secondary work when possible, but not in a way that really damages the primary work we're trying to do. So one classical policy that dates to even the 60s is called an N policy, meaning that if the queue length is below N and the system's off, we have it do nothing. It just waits until it reaches N. And then whenever it reaches that N, we turn it on and let it start doing service. And the idea here is that if the queue length is small, the queue is probably going to be exhausted quickly, so we'd like to turn it off. But if the queue is pretty large, then the queue will persist for kind of a long time, and the system can work for more time. So if we have this, then there's less time the system's going to turn off and turn on. We're not going to receive one customer, serve it, turn the machine off. Receive another customer, turn it back on, do the work, turn it back off. And so that's costly usually. If we're talking about a server or a CPU or something like that, receiving job requests. The con of this is that customers are going to have to wait if we do this. Okay, and then also our R-Quorum policy. Takes a couple of classical ideas, and it's if the queue is empty, we only do secondary work. If the queue is relatively small, below small r, we do single service to primary customers and batches of secondary jobs simultaneously. And if the queue is above r, then we service either the whole queue or big R, which is the maximum capacity we can take at a time. Whichever of those is smaller. So we can serve all the customers or at max R. So some of these ideas exist in the literature, really classical literature, but usually not combined together. The R policy, the small R policy alone existed in this paper from Newts, and Hysteretic Control is an idea that we want to keep the queue between two bounds so that it continuously works in an efficient way. And so the benefits of this is that we reduce the amount of time the primary customers have to wait while still not turning the system on and off a bunch of times, and we get some secondary work done. So this is what hysteretic control looks like. If the thing up crosses N, then we start doing work and we see that the queue starts to drop and sometimes increase and drop as customers arrive and get served simultaneously. But then we down cross below R, we tell it to just wait till it reaches N. And then that kind of repeats. Now, this does not include the secondary work that I talked about, but this is only a display of the hysteretic control idea. So here's just a flow chart of how this works. It's essentially just what I said before. We've got mode 2, which is when we do secondary work. Mode 1 is when the queue is long enough. We just keep taking big batches of customers. So we have some prior results on queue at time tau sub rho being the exit time from the mode, which is, it's like a hitting time in a sense in regular literature for probability theory or stochastic processes. So we found this kind of joint probability generating function and Laplace-Stillches transform of the number of primary, secondary customers served, the number of primary customers that arrive, and duration of the mode. We just do this with modified Z transforms. Let's do a transform, add some assumptions on the system, on the distributions of these different things, and then do the inverse after that. We can get a actually explicit formula for most of this stuff. So that leads us to moments and distributions, time distance probability matrix, ergodicity conditions, all kinds of stuff. All the basic queuing analysis that you would do for without having the real time referenced. Now then we did some more work on time-sensitive model, which gives us results depending on the real time. So here I've defined A sub t as the primary queue length, B sub t is a secondary units process in a mode. So it's still locked into a certain mode. As you can see in blue here, we have this indicator function forcing time to be within the range for the mode that we're considering. And we essentially find the Laplace transform of it, and we can do the inverse and then add some assumptions and get, in this case, time-dependent moments and marginal and even joint distributions if we use tau rho as one of the random variables. So this gives us results about the real time, but we're still locked into a mode. So what are we missing? Well, I don't want to have that blue thing there, for lack of a better term, because it locks me into the particular mode I'm considering. And I want to know what the queue length is at all moments in time if I can. So it doesn't seem that we weren't able to think of an analytic way to really approach this, but we can simulate. So this is where I'm thinking I can use the MVSP ideas. And so I'd like to optimize the parameters for efficiency, figure out where the system gets stuck so that I can, play around with these different numbers to, make the thing work more efficiently. And we so far haven't been able to quite do that, but we can analyze at least this Psi-T, which is sort of an embedded process that only updates when a service is completed. But we can do it at any moment in time. It's not mode dependent at all. So instead, we're going to study just this particular process, this drop process that we've been calling it. And it's very simple. We just plug in some parameters, simulate the thing a bunch of times, get a bunch of time series, and we can get empirical distribution at each time t. You see, this is what we get. There's a lot of intuition here, but I'm a little short on time. But essentially, we can see the distributions at each moment in time, the densities. But it's a little hard to analyze, so here's where I start using the superlevel sets and the MVSPs. And as time progresses, we move upward on that first diagram, we see where the queue is at the end of queue service, at the end of service. So initially, we start at just 10 because that's our initial queue size. And then it expands around there because customers are arriving and being served at a low rate because we've set the little r to be 20. So we're in mode 2A and 2B. And then as we move forward in time, upward, you can see that we see some patterns here. And what it is we've set the big R to be 30. So when the queue reaches 100, which is the big N, I serve 30 customers and it drops me down to 70. But there's a little noise above the 70 because there could be arrivals during that service. We see the same thing at 40. And then below 20, we see a different behavior because that other type of mode exists down there. We might just be waiting down there sometimes. And so, it's a lot more likely that we have levels below 20. So on the right, you can see the level sets, evolution over time. And this was the model without mode 2. Some similar kind of patterns, but it just does random service rather than service of batches of 30. So it's it doesn't have those clear delineations. Then the new work that we're working on now is to use probability flux across the boundaries of the MVSPs to adjust them over time. So if you look at this on top and we take that n of t to just grow over time, all it does is add oscillations. But with this thing on the far right top, that would be very hard to figure out numerically, because we'd have to sort all these things, and even if we tried to do like gradient descent to find the maxima, that would take a long time because there are a lot of them, which can happen. And if you run this forward in time slowly with small time steps as an animation, you'll see that these little polka dots sort of things, they shrink and spread, and they're going to become more of them over time. So what we want to do is use the probability of flux across those boundaries to determine how to grow and shrink them over time. And with that, I believe we're having some luck constructing these MVSPs much more efficiently, because the method that we've used, just sort of brute force sorting, is totally infeasible for large dimensions. Here are my references. So